Alright, so now let's solve for our equations, or solve our equations for tension. So from M1, the force of tension would be equal to M1A plus the force of kinetic friction. So I just rearranged this equation up here for Ft. I'm going to do the same thing for this guy right here. So F tension would be equal to M2G minus M2A. So now I have two equations, both are for the tension force. Now I can set them equal to each other. So M1A plus the force of kinetic friction would be equal to M2G minus M2A. Isolate A, so I'm going to leave the kinetic friction force on the left side, subtract M2G from it, set it equal to, subtract M1A from both sides minus M2A. Alright, so let's pull out the acceleration. So I have negative M1 minus M2. The force of kinetic friction minus M2G. So then I divide by the parentheses stuff. Which would simplify to M2G minus the force of kinetic friction divided by M1 plus M2 if you wanted to pull out the negative signs and do all that kind of stuff. That would be equal to your acceleration. Now, what about that friction force? Well, remember friction, sidebar over here, the force of friction was mu times normal. And if I go back and look at the force diagram and the equation, the normal force was equal to the M1G, the weight of the object sitting on the table. So I can make a substitution there. The force of kinetic friction would be mu M1G. So then finally, in terms of all of our variables, we get this as our answer for our acceleration. Again, this is not an equation to memorize. This is a method to learn to use. Draw a free body diagram, sum the forces, and solve. Now, if this problem didn't have friction in it, then this step with the friction in it, this equation up here, would just have no friction. That's it. So it would just be omitted. Now we can also put this on an inclined plane. So it's still a modified Atwood pulley. So here we have M1 on the inclined plane, and let's say the inclined plane is frictionless in this case, and we have two masses. Now depending on the size of the mass and depending on the angle, they may go so that M1 slides up the inclined plane, or M1 may slide down the inclined plane. The test for that I will show you. So let's first draw our free body diagram for the object on the inclined plane. Remember, switch the x-axis to be along the inclined plane. So that's your x-axis. We got a y-axis like that. So the forces acting on M1 for our free body diagram would be the gravitational force, Fg1, which is also the same thing as M1G, so whichever is your favorite. Then we have a normal force from the surface onto the object, so it has to be perpendicular to the inclined plane, so this is the force normal. Okay, and there's a string attached to it, so remember, always put your pencil on the object and trace the string. That'll give you the direction of that tension force. And for all of our problems, our pulleys are massless and frictionless, so the tension in the cord is constant throughout. And that'll do it for M1. M2 is our hanging mass. So for M2's free body diagram, we'll just have that the tension force is up and the weight force is down. Gravitational force of object 2, which is also M2G. You can choose your favorite way to write it. Okay, so this angle right here is the angle of the inclined plane, like we saw earlier with our inclined plane problems. And when I sum the forces in the x direction, so for M1, I sum the forces in my new x direction, my rotated axis x direction, the tension force is up the inclined plane, minus, remember that component of the weight force that is in the x direction, Fg sine theta. I always think of sine as on the slide, sine, slide, I don't know, they both start with S. Okay, equals MA, M1A actually. And then for the y direction, we've got a force normal pointing up away from the inclined plane, minus the component of the weight force that's holding it into the inclined plane. And it's not hopping off the inclined plane, like it's not moving in this direction. It's not moving, it's not hopping off the inclined plane, it's sliding along the inclined plane. So this would be 0. There's definitely no acceleration in that perpendicular to the inclined plane direction. And then M2, oops, there we go. Summing the forces in the x direction is boring, but I'm going to write it down because I'm trying to be a good teacher. And in the y direction, we have a tension force minus a gravitational force for object 2 is equal to M2A. Now, what I want to do first is just take a step back and say, what if this system was in perfect balance so that neither one of the objects moved? Neither one of them accelerated when we released them. So if that was true, if A is 0, then M1 times A is 0 and M2 times A is 0. Okay, so if they're in equilibrium, that is, the sum of the forces is equal to 0, then look, this tension force would be equal to Fg1 sine theta. And your tension force over here would be equal to Fg2. That's if they are in equilibrium. So I can determine if they're not in equilibrium, if this value, if Fg1 sine theta is not equal to Fg2, then the sum of the forces is not equal to 0, but the sum of the forces would be equal to ma, as per Newton's second law. So I can determine which way the objects are moving if the gravitational component of the mass on the inclined plane is greater than the gravitational force on the hanging object, then it slides down the inclined plane. So M1 would slide down the inclined plane. All right, so that's our first case. Our second case would be if Fg1 sine theta was less than Fg2. Then M1 is going to slide up the incline. So from here, you'd have to look at F1g sine theta and FG2 and determine which way they were moving based on this test right here. So which way are they moving? So let's say, for the sake of this problem, that the object on the inclined plane moves up the inclined plane. So that means that FG2 is greater than FG1 sine theta. So this is our if statement. That's just what we're making up for today. Okay, so then up the inclined plane would be the positive direction. So our tension force would be positive minus Fg1 sine theta would be equal to M1A, just using the equations that we wrote earlier. So that means that down is going to be the positive direction for the hanging mass. So our tension would be negative. Our gravitational force on that hanging mass would be positive. That would equal M2A. So again, just like we've done before, solve for the tension force here. M1A plus Fg1 sine theta. And F tension is equal to Fg2 minus M2A. Set them equal to each other. M1A plus Fg1 sine theta would be equal to Fg2 minus M2A. Solve for the acceleration. So let's isolate A. So actually I'm going to add this time, so I don't have negative signs. I'm going to add M2A to both sides. Fg2 minus subtract Fg1 sine theta from both sides. Isolate A, M1 plus M2. Fg2 minus Fg1 sine theta, and then divide by M1 plus M2 on both sides, so the acceleration would be Fg2 minus Fg1 sine theta over M1 plus M2. Now again, please don't memorize this equation. Please learn how to do the process. That's what's important. Draw the free body diagram, sum the forces, solve your equations.